Okay, well, if we can add amines to aldehydes and ketones, what would happen if we added water? Just plain good old refreshing water to aldehydes and ketones. Well, when we try to add water across the double bond, you find out if you just have an aldehyde or a ketone and you throw it in water, you've got an aldehyde or ketone floating on water. Unless it's acetone, which mixes with the water quite nicely, azeotropes the water away. But one thing we're not really getting is a reaction. So we need a catalyst. We will use either acid catalyst or base catalyst to help us add the water across the carbonyl carbon-oxygen double bond. But if we can do it, if we can add water across this double bond, we end up with the carbonyl oxygen getting a proton becoming an alcohol. So one hydrogen of the water gets added to this oxygen, leaving us an OH, which gets added to this carbon. We've got two OHs on a carbon. We call that a gem diol or a hydrate. Some people get jazzed about hydrate. I like to call it gem diols myself. That's just me. All right, however, this equilibrium for this reaction lies way, way, way to the left. Recall from good old Organic 1 that catalysts do not shift the equilibrium. They allow you to come to equilibrium faster, but adding the catalyst, the acid or the base, does not shift the equilibrium to the right. The equilibrium is going to stay at the left. It turns out we only are going to get a good reaction. We can only add water across the carbon-oxygen double bond nicely in a reaction that lies to the right if we use formaldehyde. And you should have expected that because recall that aldehydes are more reactive than ketones. And formaldehyde with two hydrogens on it would be our most reactive aldehyde. So formaldehyde is going to add water nicely. If we made this carbon a little bit more positively charged, did something crazy like put 3 chlorines on the carbon next to that carbonyl carbon, then we'd expect through inductive effects that this carbonyl carbon would have a much higher positive charge, and so we'd expect that reaction to go. But when was the last time you saw this beast in the lab? That looks scary. Okay. When we look at the numbers, when we look at our percentages here, if you have formaldehyde and you add water across the double bond with acid or base, we find that the equilibrium lies 99.9% to the gem diol. Brings to question. Remember that frog you dissected that was preserved in formaldehyde? What happened to all its water? Good question. All right, if you have acetaldehyde, 1 R group, 1 hydrogen on here, we know that aldehydes are fairly reactive. We add water to it. We see this reaction only goes 58% of the way to the gem diol. So at equilibrium, we'd have 58% gem diol, 42% of our acetaldehyde is floating in the water. If we have acetone in water, we only get 0.2% gem diol. So when you were cleaning out your glassware with acetone, you squirted some acetone in it and poured it out. What you're pouring out of your glassware was not gem diols. What you were pouring out was mainly acetone with water mixed in it and just a tiny, tiny bit of gem diol, possibly. Okay. So in general, equilibrium is not in our favor, but let's look at the mechanism of these reactions. By this time, you've probably seen a theme in a lot of our mechanisms with these carbonyl reactions. Let's first look at the base catalyzed mechanism when we have a stronger nucleophile. Note, we got a nice strong nucleophile like hydroxide in our base catalyzed hydration, and nice strong nucleophile, partial positive carbon. Lone pair on the hydroxide attacks carbonyl carbon. Pi bond breaks to make a negative oxygen up here. And then we have some water around. We get a protonation reaction. And there's our gem diol. And we get our OH minus back again. Yay, catalyst. OH minus, added water, got OH minus back. Acid catalyzed, note if we have an acid here, if we're under acidic conditions, then the nucleophile is not going to want to attack this carbonyl carbon because we don't have a very good nucleophile under acidic conditions. Recall that nucleophilicity parallels basicity. If you have a good strong nucleophile, that like hydroxide, that means it's probably a good base, and hydroxide does not exist under acidic conditions. So if you have a weak nucleophile like water, water just isn't going to attack a carbonyl carbon. That's not positive enough. However, the carbonyl carbon can be made more positive if this oxygen attacks the hydrogen of our acid, H3O+ right here. So carbonyl oxygen attacks this hydrogen, protonating that. Recall our nice resonance stabilization means we've got more positive charge on the carbonyl carbon. Water then can come in and attack that carbonyl carbon. It's more positive now, so the weak nucleophile water is like, okay, I can handle it now. And that gives us this product here. Note we had the OH already up here. We've got OH2 down here. Water comes back in, snags this hydrogen, gets rid of the positive charge by making this hydrogen-oxygen bonding pair a lone pair on the oxygen, and we have our gem diol plus our acid catalyst back again. Now, recall pKa of water 15.7 and pKa of alcohols 16 to 18 or so. What we're saying is here anything water can do, and alcohol, there's a good chance it can do it also. So what if we try to add alcohols across the carbonyl bond, the carbon-oxygen double bond of the carbonyl in aldehydes and ketones? Well, if we add two equivalents of our alcohol, we will make a group called an acetal. Note, it's going to look like an ether. It's not an ether. It's an acetal. Take our ketone or aldehyde, add two equivalents of alcohol, ROH, under acidic conditions, and we get two ORs on our carbonyl carbon. Our carbon formerly known as carbonyl carbon, and we make water. So this carbon with two OR groups on it is an acetal. Recall, carbon with two OHs on it is a gem diol. Carbon with two ORs on it is an acetal. All right, and our catalyst is normally going to be paratoluene sulfonic acid. A lot of times we would choose H2SO4, sulfuric acid, but when we're dealing with these acetals and these ketones, we probably will have some solubility issues to worry about. And paratoluene sulfonic acid, pKa of -7, conjugate base cannot be a nucleophile, so it behaves very similarly to sulfuric acid, but is going to dissolve a little bit better in your organic molecules, organic solvents. So check this out. We'll come back to this in the future. If you take this ketone here, cyclohexanone, and normally we'd add two equivalents of our alcohol, but what if our two equivalents of alcohol were connected? Here's our first equivalent of OH of our alcohols. Here's our second alcohol, but they happen to be connected here. Well, we get the carbon single bonded to the oxygen of one side of this glycol to the alcohol here, CH2, our other alcohol. We make this cyclic acetal. We're going to find the cyclic acetal. Taking a ketone or aldehyde and adding ethylene glycol is going to be very nice for us coming up in just a few minutes, perhaps on the next video. All right. So now let's check out the mechanism of adding alcohols across the carbon-oxygen double bond. As you will see, it is extremely similar to the mechanism of adding water across a double bond, as you would expect. The first thing here, we have our carbonyl. We have to be under acid conditions. This does not work under basic conditions, because if we're under base, we're going to add hydroxide and not OR. So the carbonyl oxygen attacks the hydrogen of our acid, and so we've got this protonated beast here, which is, as we saw before, resonance stabilized to give us more positive charge on the carbonyl carbon. Our alcohol, a weak nucleophile, then can attack this carbon that was the carbonyl carbon because it has more positive charge through resonance, giving us this beast here. And recall from forever, every time you have a reaction where your product has an oxygen or nitrogen with a hydrogen on it and also has positive charge, you get a deprotonation reaction. In this case, we're going to say A minus, the conjugate base of our strong acid, is going to come in, deprotonate, which means we get our acid back again. Yay, and we have added the OR group here, but note at this point we've got the carbon with our OR on it and our carbon with an OH on it. We are halfway to our acetal, and we call that a hemiacetal because calling it a half acetal would not be appropriate. But no, we're only halfway. So how do we add the other OR group? An acetal has two OR groups on here. So with our hemiacetal here, we still have more HA. Heck, that was our catalyst. We got it back. This oxygen attacks the hydrogen, becomes protonated to make H2O plus, bonded to this carbon, which is a good leaving group. Water leaves to give our positive carbon here, which is resonance stabilized. And then our HOR, resonance stabilized this way. Our alcohol, our second equivalent of alcohol, then will attack that carbon that used to be the carbonyl carbon a long time ago. To get the carbon, here's our first OR group on it. Here's our second ORH positive. The acid A minus that was made comes back in, snags that hydrogen, we get our acid back again, and then we get our acetal. So, gem-diol, 2 OHs on the carbon. Hemiacetal, 1 OH, 1 OR. Acetal, 2 ORs. Note, if you're running the experiment and you want to make this acetal, and you're starting with a ketone and 2 equivalents of alcohol, how do you do it? Easy. You take your ketone, you mix in 2 equivalents of alcohol, mix it together, nothing happens because you've not added a catalyst yet. Throw in your para-toluene sulfonic acid, stir it for a while, boom, get your acetone. So the mechanism looks a little complicated, but when you're running the experiment, it's just waiting for everything in the stew to do its thing. All right. Question though, what if we're at this hemiacetal, we're saying this oxygen is going to attack this hydrogen. Couldn't this oxygen down here attack the hydrogen? I mean, this is an OH, this is an OR. Both these oxygens are very similar in their basicities. Couldn't this OR attack the hydrogen? The answer is yes, it can. However, if this oxygen attacks the hydrogen, all that means is we are reversing our reaction and we're going backwards and we are going towards our original starting material. So both this oxygen or this oxygen, either one can attack. If this oxygen, of the OH oxygen, attacks the hydrogen, the reaction moves forward. If this oxygen attacks, the reaction just moves in the reverse direction, and Le Chatelier will tell us which way this is going to go, because we can decide. We can use Le Chatelier to decide what we're going to get here, which means if you have an acetal, here was our acetal we made before. If you have an acetal and you want to get rid of it, you want to convert this back to the ketone, just a little acid hydrolysis. Put in some aqueous acid, probably aqueous H2SO4, maybe aqueous para-toluene sulfonic acid. You will run the reverse reaction and end up with your ketone and your diol here, your alcohol. Note, we used this guy here, recall. We made this oxygen, CH2 oxygen compound from this guy. If you had this acetal here with just 2 OR groups, you could add aqueous acid and reverse this reaction to end up back with your ketone and 2 alcohols. So we'll continue with protecting groups in the next video.